is Counting What Really Counts, from combinatorics to community. So there's a lot of counts in there, and that's because combinatorics is essentially the science of counting. So we make that pun a lot. We always talk about, what is it that really counts? Um, and I want to give you my plan. This is my intended plan for the day. Here's my agenda. I'll start by telling you about my path, who I am, how I got here, and then sort of talk about what it means to be a mathematician. I know many of you are scientists, either theoretical or lab-based scientists, and there's a difference in how we function as mathematicians. And then I want to sort of close with what I consider my purpose. And this is something that I've really come to later in life, and I am now trying to fulfill my personal mission in my work. And that is more than being a mathematician. And that's the plan for the day. So the first thing I have for you is a confession. I am an accidental mathematician. I know there must be people on this call who have known from a young age exactly what it is you wanted to do in your life. You knew that you had to unravel the mysteries of the cell, or you knew you had to stare at the stars. I knew I was a good student, but I didn't know what it was that I wanted to be. I I could do lots of things, including mathematics, but I never had that drive that was like, I am going to be a mathematician in my life. And I feel like there are three people who really helped me reach that point. So the first person is my father. That's John Quinn. He was a theoretical physicist, and he was a university professor. So I knew and understood the life of a university professor. I knew the cadence of that life. And there was never a moment in my growing up that there was not belief that you couldn't do anything you wanted in this world with adequate education. So anytime I had a math question, he could answer it, and it was really fantastic. So I went off to college. I went to Williams College in Massachusetts. And I will tell you, I picked my college because it had a really great theater program. My parents were not happy with the idea of me picking a college for theater, but it had lots of good things. And it is a great school. Um, I didn't know what I was going to be when I got there. I also didn't know I had taken a math class every year of my whole life, and I assumed I needed to continue taking a math class every year in the future. So I continued taking math classes. And Professor Bill Lenhart took me aside and essentially said, Hey, you're really good at this. You should take another class. He didn't say you should be a math major. He just said you should take another class. And I always just took another class because every time he saw me sitting on the lawn eating my lunch, he'd say, Are you signed up for another math class? And I would sign up for another math class. Um, it wasn't until second semester senior year where I just needed one more class to finish a math major. I was a double major in biology and mathematics, that I took a class in combinatorics taught by Bill Lenhart. And for the first time, I was exposed to material that it just made me happy. I felt like I had intuition for it. It wasn't just that I was a good student and I could figure it out given time. It was that there was this natural instinct for how to ask interesting questions and how to go look for answers. And I knew then that if I were to go on to further education, it would be in combinatorics. And so fast forward, I spent a year as an actuary, didn't like having a real job, said, I'm going to go to grad school. And I ended up at the University of Wisconsin. And I was so fortunate to work with Richard Buraldi, who is very well known in combinatorics. He's an incredibly wonderful mentor, a kind man. Uh, when you're to the point where you're working with your PhD mentor and you go in weekly and you do your weekly meeting to show what you've accomplished, he would feed me half of his lunch. So not every PhD mentor will do that. Um, and I followed through and I studied combinatorics. And from that moment, I was truly, in my mind, a mathematician. After that, I went on, I got my first academic job at Occidental College. I then followed my husband to the Pacific Northwest, and I spent the last 20 years teaching at the University of Washington, Tacoma. Uh, I got to build the math program in Tacoma. I did academic administration in Tacoma. And as I'm doing my research and building classes, I also served my community by doing lots of work with the Math Association of America, including being the editor of a magazine, serving as the head of publications, serving on the board of directors. Eventually, I was elected president. And that was where I really understood that the impact I could have on mathematics was so much more than writing another research paper that maybe, if I'm lucky, 25 or 30 people in the world would read, or working to promote mathematics to the broader community. And that absolutely changed my focus to mathematics for all, of all ages. And when the opportunity arose, I jumped. I just recently retired from the university. I am a professor emerita at the University of Washington. And now I am the executive director of the Seattle Universal Math Museum. And my goal is to spark a love of math in each and every person from 3 to 103 with hands-on, interactive, engaging math explorations. So that's me in a nutshell. That's my path. All right. What's next? So I said these words. I am a combinatorialist. That means I think about how things are counted, how things are arranged, what the structure underneath them is, and why those patterns matter. I also really try to appreciate the beauty I see in mathematics. Mathematics often gets a bad rap. We work on the tools so hard that we never quite get to the point where we appreciate the beauty. And I would liken this to learning an instrument without ever having heard a symphony beforehand. We can appreciate music without knowing the details of music, without knowing how to produce all the sounds. And I feel like mathematics is the same thing. You can appreciate mathematics without knowing all the details. And we need more of that in our lives. And combinatorics really helped me see that. I like to understand things in a concrete, structured way. There's absolute joy and beauty there for me. It's not dissimilar from being a scientist in that there's a process of observing patterns, taking small cases, thinking about what's really going on in the small case, and then making a conjecture. I conjecture a pattern. And then the next piece is to confirm or disprove that this pattern really exists. And then you repeat until you're satisfied. And I think what satisfied means depends on your field. So for a bench scientist, I think it means that your results are reproducible by someone else, or that they have, you can reject the null hypothesis, right? There are all kinds of different ways, different standards for being satisfied with a result. But in mathematics, satisfaction, there are two kinds of satisfaction. If you're an applied mathematician, it's good enough to get the job done. Is it good enough to get the astronauts to the moon and back? That's satisfaction. To a theoretical mathematician, satisfaction really means proof. Just because the pattern's there, I am not 100% sure it goes on forever and ever and ever until I can create a proof so that it removes doubt entirely. My father, he was a theoretical physicist, and we talked a lot because theoretical physics is very much mathematics. But he would say statements to me like, Jen, I want to show you what I'm doing when I'm counting these fermions. And I know this is true for up to 10 of them interacting. I'm like, well, that's great. But is it true for 11? and he would feel that just knowing was true for 10, up to 10 was sufficient. And we would joke about it a lot. And eventually we got to the point where I helped him prove something. And there is a paper out there with two co-authors. There are four co-authors, actually, but two of them have the name J.J. Quinn and J.J. Quinn. And it's not a typo. So that's really made my heart very full. So why do I need proof? Because patterns can be deceiving, and because it looks good doesn't necessarily mean it continues. So I'm hoping this will be a little bit interactive. I'm hoping to get you doing a little bit of work. So I just want to show you what this means. I want to start by looking for a pattern. The picture says it all, but I have some words here. So given a circle, you're going to put n points along the circumference of the circle, not in a regular pattern. It's called general position. And the idea is when you draw the chord between two of these points on the circumference, we don't ever want three chords to intersect at the same point in the interior. So that would be like drawing three diameters. You could imagine they would all intersect at the center. We just want to make sure every pair of chords intersects in a different point. So if you have your points in general position, we can ask the question, how many regions, if you draw all the chords between every possible pair, how many regions does that create in the circle? So I've drawn the first five. 1 point, 2 points, 3 points, 4 points, and 5 points. And I just want you to tell me how many regions there are. So when there's 1 point, how many regions does that divide it up into?
One. Only one.
Thank you. There is not even a chord, so there is a single region. Thank you, Altair. All right. How about when I draw, I have 2 points and 1 chord. How many regions are there?
2 regions.
I love that I heard several people say that at once. Okay, how about 3?
4.
4.
All right. How about 4?
8.
8. How about 5?
16.
16. Okay. Do you see a pattern? Don't say anything. Don't say anything. What I want you to do, let's just do a little bit of a waterfall chat. Type in the comments what pattern you think you see. So, finish this sentence. If a circle has n points on its circumference, the number of regions created is, and put your conjecture in.
2 to the n minus 1.
We're not able to write into the chat,
Oh,
apparently.
you can't write into the chat? Oh, okay. Well, thank you, Henry, for saying 2 to the n minus 1. That seems to be, well, where the n minus 1 is in the exponent, not 2 to the n with the minus 1 off to the side. Okay. That's what it seems to be. And I feel, I mean, I have, this is my dad. I have 5 examples. This has got to be true. Okay, so let's go to 6 just to check it out. And I broke 6 up in a different way. If you look at the purple lines, they cordon off 6 regions. So 1, 2, 3, 4, 5, 6. So this area, this sector of the circle has 6 regions in it. And then the sector above the next purple chord has 6 regions in it. And the sector below the bottom purple chord has 6 regions in it. So now all you have to do is count inside the triangle, trying to find a nice way to count it so you know what you've counted and what you haven't counted. I'll just count out loud as I count on the inside. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I got 13 regions inside the purple triangle, plus 3 times 6 regions for the other 3 sectors. So I would get 31 regions, which is not 32. So even though the pattern looked really good and really convincing, it's not true. So, and that is why we need proof. Now, you might be wondering, well, what is the answer? I can't wait to hear. I'm looking at the question. Wouldn't it depend on how the chords from drawing a new point intersect with the regions that exist before that point? Yes, in fact, it does. But I can count the intersection points, and that will help me understand exactly what's going on here. So here's the way to think about it, and I'll just put the answer down. The number of regions, we started with 1 region, and then every time we drew a chord, if it didn't intersect anything at all, it just creates 1 new region. Okay, so I'm certainly going to have 1 plus the number of chords. And then I have to think about every time a chord has an internal crossing, it intersects something, just like Alexandria was mentioning. Every time I have an internal crossing, I'm going to add 1 more new region. So to count the regions, it's going to be 1 plus the number of chords plus the number of internal crossings. And now I just have to find a nice way to count those things. The number of chords, if you think about it, I can pick any point on the exterior. So there are n choices for that. I can pick any point aside from the first one I picked. There are n minus 1 choices for that. So I have n times n minus 1 choices, but I would get the same chord if I had picked them in the opposite order. So I would get this pair, I would get this chord by 2 possible pairings. So I'm going to have to divide that by 2. So n times n minus 1 all divided by 2 is the number of chords. Rather than I write n choose 2. I have a set of n things. I'm going to pick 2 of them. Done. That's it. So the number of chords is going to be the binomial coefficient n choose 2, which equals n times n minus 1, all divided by 2. The number of internal crossings is actually pretty fascinating. And I claim that every 4 points has exactly one internal crossing. And we can see that. I'm going to go back up page here. If I pick 4 points, if I look at when there are 4 points and I draw all the chords, you can see that there's only one crossing for these 4 points. And this image is replicated for every 4 points you choose. So what that means is the number of regions will always be 1 plus n choose 2 plus n choose 4 is the number of ways I can pick 4 elements from an n element set. So that's the answer. And for small values, it looks like 2 raised to the n minus 1. But once we get to 6, we're missing 1. So I think that's pretty cool as an example of just because we see the pattern, it doesn't necessarily continue, and we need to have a proof. Okay, so what do I really do? That's something I do in a class. What is it that I really do? I like to look at identities, ideally these things called combinatorial identities or algebraic identities, and I like to come up with a concrete counting context to understand them. So I'm going to pick one of my favorites. This is the sum of binomial coefficients. N is a fixed number someone gives me that's non-negative. So n choose 0 just means select, you have a set of n things and I don't want to pick any of them. Well, there's only one way not to pick any of them. The answer is going to be 1. N minus 1 choose 1. That's now I have a set of n minus 1 things. I'm going to pick 1 out of it. Plus n minus 2 choose 2. I remove something, I pick 2 things. And I want to add all these up. And notice here I have dot, dot, dot. At some point, n minus k, when k is bigger than half n minus k is going to be bigger than k. So if I were to say, I have a set of 10 things, and I want to know how to create a subset of 12 of them, you'll go, that can't be done because I don't have enough objects. So even though this looks like it's an infinite sum, there becomes a point where these terms are essentially meaningless. They're 0. So it really is a finite sum. So we're looking at a finite sum that has some pretty symmetry to it in its own way. And the sum is equal to this thing I've called f sub n. F sub n is one of my favorite number sequence. It stands for the Fibonacci numbers. So here is a sum of binomial coefficients equaling a Fibonacci number. If you wanted to know the computation for n choose k, again, we have a set of n things and we're selecting k of them. The answer here is always going to be n factorial divided by k factorial times n minus k factorial. So we can compute it, but for me, what it represents is the important thing. And here, the binomial coefficients, have you seen, Pascal's triangle? When you expand a binomial like x plus y raised to the nth power, you start with 1s on the exterior, and then to get to the next value, you add the previous 2 and the line above it. So 1 plus 1 is 2, 1 plus 0 is 1, 1 plus 2 is 3. And these coefficients become the coefficients of the binomial expansion. So if I wanted to know what x plus 1 raised to the 6th power was as a polynomial, I could just read the coefficients off here. It would be x to the 6th plus 6x to the 5th plus 15x to the 4th plus 20x to the 3rd plus 15x squared plus 6x plus 1. And this is something back in algebra days, right? So hopefully this is familiar to you. And what this identity means is if, as I look at Pascal's triangle, whoopsie, and I add on this diagonal, so 1 plus 7 plus 15 plus 10 plus 1, that adds up to 34. And that actually ends up being the 8th Fibonacci number. I'm not going to assume everybody knows what a Fibonacci number is. So let me just introduce them for a minute. This is a sequence of numbers that starts with the initial conditions. F0 is 1 and F1 is 1. And then to get the next number in the sequence, we're going to add the previous 2. So to get F2, I'm going to add F1 plus F0. So that would be 2. And then to get, so we get 1, 1, 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 3 plus 5 is 8. 5 plus 8 is 13. And we can keep going on. This is a sequence that there are entire books devoted to this sequence. And there are beautiful patterns within this sequence, including the one we're looking at right now. So I want to count the Fibonacci numbers. I want them to physically represent something. And what I claim they count are the different ways I can write the number as a sum of 1s and 2s, where the ordering of the 1s and 2s matter. So to write 1 as the sum of 1s and 2s, I can only do that one way. To write 2 as a sums of 1s and 2s, I can do that as 1 plus 1 or 2. These are called compositions of a number. To write 3, it could be 1 plus 1 plus 1, or 1 plus 2, or 2 plus 3. So there are 3 ways to write 3. There are 5 ways to write 5. There are 8 ways to write 8. So you can see all these numbers match the Fibonacci numbers. And we just have to make sure it matches the recurrence relation. And if we think about it, either my composition starts with a 1, and then I need a composition that adds up to n minus 1. So that's Fn minus 1. Or the composition starts with a 2, and then I would have to add on to it a composition of n minus 2. So that's the sum of the previous 2 numbers. So we have the same initial condition, and we satisfy the same recurrence relation. So this model really represents what the Fibonacci numbers are. So the answer here is that for Fn, it is counted by these compositions of 1s and 2s. But compositions is one of these words that needs to be defined, and people are like, oh, that's why math is hard to get to. We create specialized vocabulary that you have to learn to have entrance into it. So instead, I'm going to replace the 1s and 2s by squares and dominoes and change my question to be how many ways can I tile a strip of length n, a 1 by n board, with squares or dominoes. So 1 by 1 squares or 1 by 2 dominoes. So wherever you have a 1, you just put a square. And wherever you have a 2, you put a domino. And each one of these compositions becomes a square domino tiling. And I love using square domino tilings to understand identities, that involve Fibonacci numbers. So I'm going to do, this is the one proof I'm going to do for you today. And it's a classic combinatorial technique of asking a question and answering it in 2 different ways. So the question I'm going to ask is how many square domino tilings exists of a 1 by n board using square dominoes, using squares and dominoes. So we just saw that the first answer to this question is just the nth Fibonacci number. So we're halfway done. We only have one more answer to come up with. And I really love this answer. So K is my index here, and it's going to represent the number of dominoes in a tiling. Okay, so I'm going to break all of the tilings of the board of length n into the tilings with no dominoes, the tilings with one domino, the tilings with two dominoes, all the way up to the tilings with n over 2 rounded down dominoes. What if I allow ones, twos, and threes? That's a different recurrence relation. It gives you different numbers. People do study them. They are called Fibonacci numbers. And there's so much you can study, but that's a wonderful question. That is absolutely a mathematical question to ask. What happens if you change your parameters? So if K represents the number of dominoes in the tiling, let's count how many tilings there are. Okay, there's a lot here, so I'm going to break it down step by step. If K dominoes are used, we know that they cover twice as many cells in the tiling. So if I have 4 dominoes, I have 8 cells that are covered by the tiling. So I'm covering n cells total, which means everything else has to be a square. So n minus 2k has to be the number of squares that I'm using in this tiling. And so the number of tiles, regardless of whether they're a square or a domino, is going to be the sum of these two numbers, k and n minus 2k. So the total number of tiles I'm using is n minus k. So imagine this is the first tile, the second tile, the third tile, up to the n minus kth tile. To get a tiling, all I have to do is tell you which of these n minus k tiles are the dominoes. So I can pick a set of positions. I can pick a set of k positions from the n minus k tilings. That happens to be the binomial coefficient, n minus k choose k. So I pick where, this is one set of positions I've picked. That gives me the tiling because I put the domino on the positions I pick, and then I fill the rest of them with squares. Okay, those don't look like squares, but you get my idea that I'm changing the tile to be a specific square. That's one tiling. Each set of k subsets of size k will give me a different tiling. So n minus k choose k represents the number of tilings with k dominoes. And now all I have to do is add them up for all possible k. Well, that's the left-hand side of this equation. N choose 0 plus n minus 1 choose 1 ... until it becomes 0. And that is like a classic combinatorial proof. You can do half of the things in this world combinatorially with this technique, and it's one of my very favorites. In fact, I have written an entire book called Proofs That Really Count, The Art of Combinatorial Proof, and I would say 80% of the proofs in that book use this technique. The whole first chapter is on just using Fibonacci numbers. And you'll notice, you might not be able to read the words on here, but the sum here has binomial coefficients, Fibonacci numbers, Lucca numbers, linear recurrences, so you can use different tile lengths, and then other ideas through there. I wrote it with Art Benjamin, who is a professor at Harvey Mudd College and a dear, dear friend. So what do? We investigate stuff, we create our level of evidence, which for mathematicians is proof. We write papers, we write books, and we involve undergraduates in our work when we can. So that's the insight into what it's like to be a mathematician. And I will be completely honest to say that considering I didn't know I had a passion for this when I started, I have accomplished more than I ever dreamed possible. So I've had a 30-year academic career. I've raised an amazing family. I have served the Mathematical Association of America in a very meaningful way. including being president during the pandemic. And I really felt it was my role to help our whole profession transition to remote teaching, because that happened to be something I was already doing, and was happy to share my knowledge. So it was sort of being the right person at the right time. Um, Proofs That Really Count has won a couple of awards. But on top of that, I have been recognized as a scientific artist, both for biological art that I do with my husband. We he is the microbe wrangler, and I paint with his microbes, and we use bioluminescent bacteria that grows on its own, and then the art glows on its own. So that's been pretty fun. And really, this is me discovering my passion, which is I want to serve my community and mathematics through mathematics, through promoting mathematics. So I was looking at Altair's comment, and yes, there are so many ways you can prove it. I will say that if you look at Pascal's identity that you're talking about, that's going to be an algebraic proof. So you are going to end up doing some algebraic manipulation, and that's a beautiful proof. I don't disagree, it's a beautiful proof. But for me, it removes some of the intuition as to why it might be right. So when you can see it happen in a concrete way, when you can understand what it counts, it's a different kind of proof to me that has a beauty that I like to see moving forward. Okay. So I want to serve my community. And what does that mean? I'd love to let you know about the Seattle Universal Math Museum. I have been working here for a year and a half, maybe 2 years almost. The museum has existed now for 6 years. It was founded in 2019 by Tracy Drinkwater. And Tracy wanted a place to have math field trips for students, for elementary and middle school students, to come and really experience math in a positive and creative way. 2019 was not a really great time to start a hands-on interactive museum when a year later we were all going to go into isolation. So it's taken a little while, and coming out of the pandemic, the decision was made to try outreach. We have been traveling to schools to do math festivals, to do hands-on lessons in classes. We have been partnering with local museums. We've been doing pop-ups at farmers markets. We're bringing math. We're bringing math to the people. We're meeting them where they're at with hands-on interactive activities. In 2005, we did 374 events, and we met 23,000 people just through our outreach. And as of last month, like just a month ago, we had the grand opening of our first ever public visitor space. So this is a picture at our grand opening. You can see there are tons of people here playing with math concepts, doing origami. It is amazing. This is the beginning of seeing the dream realized. And I feel like everything in my life has led me to this moment, whether it's my writing, whether it's my public service, whether it's my administration, whether it's my mathematics. It's all used in service of bringing math to the community. And I couldn't be happier with what I'm doing and the impact that it's having on the community. Because remember, what got me to be a mathematician were people who encouraged me, who kept me excited, who kept saying, you belong here. And I want what this museum does to be a place where we spread that message to everyone. The truth is, you don't have to be that eccentric genius that we see in the movies who are the mathematicians. I want to convince people everyone is a mathematician, especially if you're someone who appreciates patterns and starts counting things. Anyone can be a mathematician if you ask those mathematical questions, like what happens if you use something that's not a square and a domino? Those are exactly the kinds of questions that mathematicians ask. How do we change the parameters and find something new? And if we can create that excitement from the very beginning, then maybe we don't have to remediate the trauma later in life, which is what I think half my time was teaching at the university. Somewhere in someone's life, they had experienced math trauma and it prevented them from making progress towards their dreams. So with that, I see my time is up, and I will just say thank you. And here's how you can contact me if you have any further questions. Well, there are questions here, which I will happily answer, but also in the future.
Thanks, Jenny. Yeah, feel free to come off and ask any questions that you might have left after that. I'm still unsure about it, but so I'm looking to learn from everyone. If you have anything to ask Jenny, now's the time.
It was so clear. You have no questions.
Hi, I have a question.
Sure.
I was wondering, in your outreach and your work with kinds of hands-on interactive projects, what kinds of math questions have you found most effective at engaging people of different ages?
We try to have what you would call low floor, high ceiling questions. So things that you can just start playing with and not realize what you're doing is mathematical. But embedded in it are questions that you can ask later on. So the whole gamut. Things in geometry are actually really lend themselves to that. I didn't wear those earrings today. There's some really great tiling questions out there, including what shapes can you use to tile the plane? So some people just want to come and create and make a pretty tiling, right? Other people will engage and go, I can do it with triangles, and I can do it with squares, and I can do it with rectangles. And if I'm Escher, I can do it with horsemen. So I don't know if you're aware of the question of the monotile that was resolved recently. Well, maybe 2022. It was resolved by David Smith and Chaim Goodman Strauss. So the question of so there's lots of tiling questions you can ask. And, we have tiling questions from, can you make this tangram? Start with a tangram. Can you fill it in with the tiles we have? There are things called 21st century tiles. And that can engage a 3-year-old for a really long time. And they're just talking about what the shapes are. But then you can have really interesting frames to have other people try to fill in that are pretty hard. We also have bubble tiles. Love bubble tiles. Bubble tiles are based on a circle broken into six sectors. And the sector either has a convex or a concave curve. And the bubble tiles, we have all the different possibilities for bubble tiles, how you could arrange them, or how you could put the sectors, concave versus convex. And there is the challenge. Here is a frame. Can you create one of a kind? Take one of each kind of bubble tile and fill in the frame. So that's sort of a classic puzzle. Well, it's a new puzzle. And there are 15,000 solutions that someone has gone and simulated after learning about bubble tiles, or more than 15,000 solutions. But I can tell you, it took me a day and a half to find my first solution. It was not an easy, even if there's so many solutions out there, but we start to ask the questions. We didn't know how many solutions there were to begin with. It's like, here's one, here's a new one. And every time someone found a solution, it ended up being different. So that would lead me to suspect there are many solutions. And that became a project for someone to work on, how many solutions are. But a little kid can come in and start playing with bubble tiles and start making flowers with bubble tiles. The Einstein, the one tile, the question, if you're not familiar with it, is that can you find a tile, a single tile that tiles the plane in an aperiodic fashion and cannot be used in a periodic tiling. So a periodic tiling is you have some shape, some general shape that then can then be replicated around and around and around to make your wallpaper pattern. And the story, the history of the monotile question, it's wonderful. I mean, the first answer was, yes, you can do it. And here's my tile. And it has many disconnected parts to it, right? Do you call that a tile? If it isn't all in one piece, is it a tile? But there are like 17 pieces, and that 17-piece set could be used to create the aperiodic tiling. And then Penrose came up with the kite and dart tiling that is an aperiodic tiling, right? So it's like, well, I'm close, but I'm not quite there. And here's my solution. So sometimes you answer a different question. And when David Smith found his tiling, which was initially called the hat and the shirt tiling, one of them looked like a shirt, like a Hawaiian shirt. It was called that because the hat was the chiral version of the shirt. So it's the same tiling, it's just a different version of it. So is this the same tiling as that if I have to use them in, it depends on what your definition of one tiling is. So that was just news to come up with. Here's one tile. I know we have to flip it every now and then. And then they worked on what other shapes, and in the middle of transforming from the hat tiling to the tortoise tiling, in the middle, they found what they call the specter tile. And the specter tile is, you don't have to use the chiral version. It is symmetric. I was like, big, done, huzzah. It really has been definitively answered. But in that whole period of time, there were so many interesting takes on the questions. And you can see that's a tiling question that people can appreciate. So the kids will just play with the specter tiling. And it's hard, I'm going to say this, it is hard to create the specter tiling without understanding. If you just start trying to put it together, you get little holes. It's like, how do I fill this hole? And you have to understand, you create a larger version of the specter tile from the specter tiles. And that's sort of the fractal nature of the tiling. So the shape of the tile grows. So I take little specters to create a mid-sized specter, and then I take mid-sized specters to create a bigger specter, and then I take bigger specters to create an even bigger specter. And that's how you know that it's not periodic. Because if it was periodic, there would be a maximum size, right? if this is the biggest size of that shape that got made, then that should be repeated all around. And I shouldn't be able to then create a bigger one even still. So that's sort of how you know what you've got is aperiodic. Long story short, tilings are great. Tilings are great. Geometric deconstructions are great. Chaos is great. We have chaos games. We have like a fractal tree exhibit. Origami is great. People can come in and fold and just talk about shapes, or people can come in and we talk about the symmetry groups needed to design a good hexaflexagon. You know, there's so much you can do, and I can't wait to develop more.
We had one, excuse me, question in the chat. Do you know of any interesting applications of combinatorics to life physical sciences?
Oh, wow, to life physical sciences. I think everything is an interesting application of combinatorics. Life physical sciences. There are some applications. I mean, combinatorics is the basics of all cryptography systems. And I would say some of the combinatorics problems get too big too fast. So I would almost go the other way around, that there are some interesting life science applications to combinatorics are really interesting. So there were people who were trying to use DNA to solve the traveling salesman problem in a test tube, because I don't have all the details off the top of my head, but they were literally using biology as the computer to search for solutions. And I thought that was pretty cool. My favorite, now this is going to be a crazy one. My favorite silly application, it's like so obvious, you don't feel like I'm saying anything profound, but it has surprising applications. Is the pigeonhole principle. Simple idea. If you have 10 pigeons and 9 pigeonholes and they all fly home, the conclusion is there is some box that has at least 2 pigeons in it. There might be a box that has all 10 pigeons in it, right? But that box has 2. So that satisfies the answer. But there's no way you can distribute the pigeons and not get a repeat in some box. And that very simple idea has some really profound consequences, including, things like the party problem, where, if there are 6 people in a party, is that the right number? 6 people in the party. If you have at least, then they're either 2 people who are mutual friend, or there are either 3 people who are mutual friends or 3 people who are mutual enemies. So there are hidden patterns in randomness that occur because of the possibilities in combinatorics. So just saying. All right, let's see. There are lots of questions in here.
The next one is, what does research on combinatorics look like these days? What topics, theorems are being explored?
That is a wonderful question. There are so many answers to it. There are so many places people are doing research. And I will say combinatorics started as a proof technique. People used to say, oh, that's just a technique. It's not really a field in and of itself. And I don't know if you've ever heard of a mathematician named Erdős. Paul Erdős was an unusual man. He was an itinerant mathematician, and he would show up at someone's doorstep ring the doorbell and say, my brain is open, he would expect you to host him, and he would then talk to you at all hours of the day or night about mathematics. And he just created so many questions that people are interested in solving. And if you've ever played the Kevin Bacon number game, it's like, how far is a particular actor or actress from Kevin Bacon, where the distance is by has been in a movie with. So someone who has been in a movie with Kevin Bacon has a Kevin Bacon number of 1. And someone who's been in a movie with someone who's been in a movie with Kevin Bacon has a Bacon number of 2. Well, that actually started with Erdős. So we talk about Erdős numbers, with your distance to Erdős being how far it takes for you in collaborations on papers to get to an Erdős number. And at one point it was, you are either connected to Erdős in less than 5, or you haven't written a paper yet with a co-author. So I would love to tell you what's cutting edge in combinatorics, and I'm going to be completely honest, I am not keeping up because I'm focusing on a museum. There's that's just the truth of it. There's only so much time in the day. Okay.
If there's time, can I ask one more question?
Absolutely.
Okay. I was wondering how you think about kind of bridging the gap between those sorts of like intuitive understanding and igniting curiosity in people. And then there's kind of a point where someone needs to engage with that more formalized language and all of the kinds of levels of abstraction that might be more off-putting to somebody who hasn't done a lot of math. And I guess your thoughts on kind of bridging that gap between somebody who might be interested in this, but finds looking at a math paper very daunting.
Well, that's because reading math papers is daunting. When I was taught to write papers, and I was taught to write papers by a very, very wonderful expositor, it's like, what's the absolute minimum I can put in this paper? What are the fewest number of breadcrumbs I can add so someone can follow the argument? And I think we're doing a disservice to saying, when I go to I went to a matrix theory conference recently, and can I tell you, 3/4 of the talks were horrible. People just thought their one idea was so important that I should know why it's important. And they need to tell the story of why it's important to convince me of it. They need to give me the definitions to convince me that it's worth my time to learn that specialized language. Now, half the people in the room already knew it, but we're not going to make progress until everyone can engage in it. And we make the assumption that everyone can engage in it, right? So I know that, and I know this is a hard sell, I know that mathematical language is exclusionary. I know that when I am writing a paper and I'm trying to figure out in my mind clarity so that someone can follow why the argument works, I find it is so hard to meet the academic expectations and satisfy my own personal sense of this makes sense. And I'd like to think, as a discipline, we have to change our discourse and we need to tell more stories. And I understand that's not the prevailing thought. So yes, we need to we need to show how that intuition helped to get us to the answer rather than just showing what the answer is. So even when you're reading a textbook, students don't read textbooks because it's hard. It's hard to read the textbook because it's showing me the answer. And lots of times, the struggle to get to that answer was real. And it took a long time to understand why that's the right approach. And helping people understand the big picture is so important that we need to do better at that. I mean, the discipline needs to do that. So I think if we can create the excitement and tell more stories, then we can help work towards the formalization that is required of us. But we have to understand the why. I will say I have a son who's in graduate school right now in his first year. And he is, I love that he's complaining to me. He's like, my professor's brilliant, but I don't understand why we're doing this. I'm like, okay, you need to change that. That's okay.
Thank you.
Thanks for asking the question.
Jenny, you can definitely see how passionate you are about the work that you do. Thank you so much for joining us today and engaging in this conversation. And just for the folks still on the line, our next Curiosity Lab, which is the second Sunday of May, is in the complete opposite direction of math. It's the search for life, exploring the permeation of chlorine dioxide gas on Mars and its effects on complex biomarkers. That was a mouthful. I hope you can join us next month. And thank you again, Jenny, for sharing your passion with us today. And enjoy the rest of your day, everyone.